Hello everyone, welcome to Recitation session for CEE222 Water Resources Engineering. This is the recitation for week 9. So this week we will have 5 different questions and they are actually pretty short. So let me get started with the first one. This question is 6, 3, 4 in your textbooks. First let me read the question. A concrete open channel is required to pass a flow rate of 42.5 cubic meter per second. And we need to design the base hydraulic trapezoidal section for the channel. So for this question, you will actually need to check your textbooks, page 209, 8 and 209. In this page you will see example 6.4. So this example will give you the best hydraulic section for a trapezoidal. So according to this page you will see information and you will see the example. Based on this information, the most efficient trapezoidal section is half hexagon, and this means that we have 60-degree angles on both of these sides, 60 here and we have 60 here. Or in other words, this means that the m, which is the slope here, is square root of 3 divided by 3, and this is actually coming from code 60. So knowing that, we will move forward and we will find the depth of the channel and we will find the width of the channel. So again, from the example, the B, which is width, is equal to this value, which is 2 times square root of 3 over 3 multiplied by y, which is depth. So from here we can get 1.15 y. This is equal to B. And also from table 6.1, you will see the area and perimeter of trapezoidal channels. So the area is this value and the perimeter will be this value. So to find the depth and width, we are going to benefit from these equations. So from here, if we use B in this equation as 1.15y, we will get area as 1.73 y square. And also similarly, if we use B here as 1.15y, and we already know the value of m, which is this value, so from here we will get P is equal to 3.46y. So after that, actually it will be pretty easier because we already know the flow rate and we know the area and perimeter in the form of depth. So if we write the Manning's equation, let me write it here. So we had 42.5 cms which is equal to 1 over n, which is Manning's n coefficient, and it was given as 0.013. And then we will have hydraulic diameter, which is A over P. So we have 173 y square over 3.46 y. After that, we are assuming that the slope is 0.01. And finally, we will have area, because this is Q. And until here, this is the part of velocity. And then we will have area, which is 1.73 y square. So as you can see, the only unknown here is depth, which is y. So from these calculations, we will get y as 1.84 meters, and the width will be 2.12 meters. And you can get this value from this equation, since we already know the y, or you can just directly use it here. Okay, question 2, 6.4.2. So in this question, it starts with an information about determining the flow classification, such as subcritical, supercritical, or critical flow. So first of all, we can find it using Freud number, which is NF, or we can calculate the critical depth, which is YC, and then based on our depth, which is 1.2 meter here, we can calculate if it is subcritical or supercritical or critical. So first of all, I will give this information. So if we have Freud numbers less than 1, we have subcritical. If it is equal to 1, this means we have critical flow. But if it is higher than 1, then it means we have supercritical. For the critical depth, if we have y, or y is higher than critical depth, this means we have subcritical. If it is equal to critical depth, of course the flow will be critical. But if it is lower than critical depth, this means we have supercritical. So the question asks us to find the values in example 6.1, which are here, and we actually have flow rate as 25.3 cubic meter per second, and we have a normal depth as 1.2 meter. So we need to find the classification of the flow using both of these approaches. So let me get started with the first one. So the Reynolds number is equal to velocity over acceleration times hydraulic depth. So if you check your textbooks, I think it's also again table 6.1. Here you will see hydraulic diameter, not hydraulic depth. You will see hydraulic diameters for each of the flow, each of the channels, like rectangular, trapezoidal. So based on this table, hydraulic diameter for rectangular is equal to y. So you can just directly use y here. And here we don't know the velocity currently, but we already know the flow rate, so we can calculate velocity from here. So we will have Q divided by area. We have 25.3 over area of this channel. So this gives 7.03 meter per second. And if you replace this here, 7.03 in the root of g, so it will be 9.81 times hydraulic diameter, and this is giving 2.05. So when we check these conditions, since it is higher than 1, we will have a supercritical flow if we check the flow classification based on the Freud number. And now for the second one, again, if you check your textbooks, you will find an equation, and I guess I also showed that in previous recitations. So to find the critical depth, we could use this equation. Which is square of flow rate over the gravitational acceleration times b square. So this actually gives unit discharge Q over P, but you can also use that like this in this form. So if we do the calculations, we have 25.3, we have 9.81, and we have width, which is 3 meters. From there we will get 1.94 meters. And now we are going to check that. So we have critical depth as 1.94, but we have normal depth as 1.2. So again, we can confirm that the flow classification is supercritical. Okay, question 3, 6.4.4. Let me first read the question. So here we have a flow of 834 cubic feet per second, and we have a 10 feet wide and 6 feet depth rectangular channel, as you can see here. So here we need to find a few things. First of all, we are going to find specific energy of the channel. The second one, we will determine if the flow is supercritical, subcritical, or critical. And finally, we are going to find the slope must be provided to produce a uniform flow at this depth. So we have flow rate given, and we have Manning's N coefficient given. Again, we will start with calculating the velocity, because we need that for determining the Freud numbers and also for Manning's equation. So let's say V is equal to Q over area. This gives 13.9 feet per second. And then to determine the Freud numbers, what we need to do is divide velocity by gt, and this was gravitational acceleration, and this is hydraulic diameter. Again, from table 6.1, you can see that the hydraulic diameter will be equal to y. So we have 13.9. We have 32.2 feet per square feet over square second, and for hydraulic diameter we will have 6. So this is going to give exactly 1. So this means that we have a critical flow. So we are done with the type of flow. Then we can calculate specific energy. Specific energy is actually v square over 2g, so which is velocity head plus the depth. So we have velocity here, which is 13.9 square over 2 times 32.2 feet over square second, and this is going to give, and we have depth here as 6 feet. This gives 9 feet of specific energy. And the final thing is we are going to find the slope. And since we already know the flow rate and we already know area, perimeter, we can just use Manning's equation. So the flow rate is 834 is equal to 1 over 0.014 times we have area as 60 square feet over perimeter. We have 10 here, we have 6. Then we will have slope, which we are going to find. And again, the area, it's also 60. Oh, actually, since this is in British units, we need to have 1.49. So from here, we can get slope as, let me write here, slope as 0.00448. And actually, let me write it here. And this gives the slope. So we are done with all the requests. Let's continue with question 4. This is the question 6.4.7. Again, we have a very similar question to previous ones. Again, let me start with the question text. So here we have a trapezoidal channel, and it conveys 480 cubic feet per second water. The depth of the water is 8.3 feet, and the bottom width is 10 feet. And we have side slopes as 1, 1. So we need to find the flow classification, we need to find the specific energy, and we need to find the critical depth. So first of all, to find the flow type or flow classification, we will start with fluid numbers. So we had velocity over GD, which is acceleration and which is hydraulic diameter. At this point, you may need to check table 6.1 for the value of hydraulic diameter for trapezoidal channels, because it was only the water depth for rectangular channels, but for trapezoidal channels we will have different hydraulic diameters. So first of all, according to table 6.1, the hydraulic diameter is equal to area over top width. Therefore, we need to find the area first, and then we are going to find that. Then we will find the hydraulic diameter. So here the area is this is formula, and the top width is P plus 2my. And since we know the width as 10 feet, and the depth is 8.3, and m was 1, and this is going to give, we have 152 square feet, and we will have top width So we found top width as 26.6, which is the width of this distance from the top of the channel. And so this is giving 5.72 feet. So we found we calculated the value that we need to find for numbers. And again, we can calculate the velocity. So the flow rate is 480, and the area is 152. And it is actually giving 3.16 feet per second. So let me write everything on this equation. So we have 3.16. We have 32.2 feet over square second, and we have D as 5.71 feet. And from this calculation, we can get for number as 0.233. Yes, it's 3. So this means that we have a subcritical flow. Because if you remember from the second question, if the first number is lower than 1, we will have subcritical flow. Otherwise, it will be supercritical. And we calculated the flow type. The second request is determining the specific energy. So specific energy was the velocity hat plus the depth of the water. The velocity is 3.16. We have 2 times 32.2 plus we have y, which is 8.3. And this gives the specific energy as 8.46 feet. And we calculated the specific energy here. And finally, now we need to find the critical depth. But the question says that we need to find the critical depth using figures. Let me use another color. Use figure 6.98. So if you look at your textbooks, you will see a graph like this. Then we will have values here, and we will have values here. So based on the value on the x-axis, we can calculate this side or vice versa. So here we need to find QM over G and width. And this is actually giving 0.267. So this value is actually right here. So you will match this value. For example, let's say it's around here. After that, on the y-axis, we will have myc over b. So we have a curve, and based on this value, we will have a corresponding value for myc over b. And from that, I can use here this value myc over b is equal to 0.36. So it's just a basic process. Based on the value on x-axis, we are calculating the value for myc over b. And in the question, we are requested to find the critical depth. And we already know the m, which is slope. It was 1. We have width as 10 feet. And, oh, actually, you cannot see that. So let me write that again. So we have myc over b equal to 0.36. So this was 1. This was 10. Therefore, this gives critical depth as 2.6 feet. And we calculated the critical depth as well. Now we are at final question of the week 9. The question number is 6.4.10. So in this question, we have these two channels with width of 13 feet and 6 feet. And in the middle of these channels, we have a transition channel with 100 feet long. So basically, this transition channel is connecting these two channels. So that in this transition channel, we are going to need to determine the change in bottom elevation, and we are going to determine the water surface profile. Here we have a design discharge as 500 cubic feet per second, and we have Manning's N value as 0.013. The slope is 0.009, and as I mentioned, we are going to need to find change in bottom elevation, and the head loss is given as 1.5 feet in this transition channel. So let me write that. So let's say this is inlet and this is exit. So we can take these points. We can take this point as reference and also this one, so that we can calculate what's going on on this channel, on this transition channel. So this will be inlet and this will be exit. So if you check your textbooks, you will find this equation 6.26a. So it says that this is the bottom elevation at inlet. We have water depth. Also in inlet we have velocity. And now we are going to this part, which is the exit from this transition channel. And we have water depth, we have velocity head, we have head loss, of course, and we have bottom elevation. We have head loss on this part because this is the inlet and this is the exit. There will be some head loss throughout this way. So, having this equation, we need to find the depth and also the velocity in these channels. Actually, this can be this misleading. So let's say this is width. It looks like a depth, but it is not. And this is also width. So that we need to find the water depth. And let's say normal depth inlet and normal depth exit. So we have Manning's equation again. And since we already know the flow rate, 500 is equal to 1.49, 0.002, 0.02, 13. And since this is rectangular, the area will be 13 feet times y. Over the perimeter. It will be 12 plus 2y. Slope was given as 0.0009 and the area again 12 times y. And this is for this channel. And for the second channel, which is here, we just need to change this part and also this part. So let's say the width was 12 and now this width will be 6. And also this will be 6y. So let me write that. This is for inlet and this is for exit. Okay, based on these equations, we can calculate the water depth in both of these channels. So from the inlet equation, YE is equal to 5.88 feet. And at exit, YE is equal to 13.4 feet. And let's continue with these depths. So since we already know the water depth and since we already know the channel width, we can calculate the velocity. So the velocity will be coming from Q over A. So for example, for this one, it is 500 over 588 times 12. And this will be 7.09 feet per second. Similarly, the velocity at the exit will be 6.23 feet per second. So let's talk about why we calculated these depths and these velocities. Even though these are specific for these channels, since we will have the same condition at this point and at this point, we can use these values as the inlet of transition channel and as the exit of this transition channel. So at this point, the water depth is 5.88 and the velocity is 13.4. And similarly, at this point, the water depth is 13.4 and sorry, the velocity is 7.09 at this point, and water depth is 13.4, and the velocity is 6.23 feet per second. So we can now consider using this energy balance equation. So let's write what we know. So first of all, we know that it was 5.88 feet. Here we also know this is 7.09 square over the gravitational acceleration. And on the right hand side, we have YE, which is the depth at the exit of transition channel, and this is 13.4 feet. The velocity head is, we have 6.23 feet per second over 33.2. And finally, and additionally, we had the head loss, which was already given as 1.5 feet. Okay, so we wrote everything we have except the bottom elevation at ZE here and also ZE. So here we can make any assumptions because we don't actually need to find the actual bottom elevation for this part and this part, but we need to find the change in bottom elevation. So we can take either point as the reference. So let's take this as the reference point so that we can assume that the channel bottom elevation at this point is 0, so that we can calculate the change in bottom elevation. So you could do the opposite direction, but we can go with that. So based on this equation, and since we already know everything, we can calculate ZT. So it is calculated as 8.84 feet. So this means that actually we have higher bottom elevation and it is getting decreased to the exit. So we will have something like this. And of course the shape can be misleading again, but this is just showing the bottom elevation change. Okay, and now we calculated the change in bottom elevation and we need to find water surface profile in this transition. And let me clear this, then we will create a table to show the water surface profile. Okay, now let's continue with this table because we needed to find water surface profile in this transition channel. So to do that, I wrote everything we have so that we can calculate the width, the channel bottom elevation. We have energy head, we have total energy, we have specific energy, and we have water depth. And we divided this transition channel into 5. So we have inlet as here, which is 0 feet. And let's say we have 25, we have 50, we have 75, and we have exit, which is 100 feet, which is the exit of the transition channel. So let's get started with what we know. So this was already given in the question, which is the width of the inlet channel, and for the exit it was 6. We calculated the bottom elevation is 8.84, and since we took exit as reference, it was 0. And now we are going to calculate the total energy, and it is the velocity head plus the water depth plus bottom elevation. So for example, if we calculate it for inlet, we will have 7.09 square over 2 times 32.2 plus the depth was calculated as 5.88 feet, and we had bottom elevation, so it was 8.84. So from here we will get 15.5 feet. This is the total energy for this inlet of transition channel. And to calculate the specific energy, if you remember, the specific energy is only this part. So if we remove the bottom elevation from this equation, we will get 15.5 minus 8.84, which is 6.66. And the depth was already found as 5.88. Similarly, we can do that for the exit. So for the exit, we have velocity as 6.23. This part will be same. We have water depth as 13.4. Actually, let me write that. So this is for exit. So we have 6.23. We have 13.4. And we had 0. So the total energy at the exit is 14 feet. So let me write that. And as I mentioned, we needed to remove the bottom elevation from this equation to calculate the specific energy. Since it's already 0, we will have 0 again. And finally, the depth was 13.4. After this point, it is just linear interpolation, because as stated in the question, it is uniformly distributed throughout the transition channel. So for example, let's say we have 6 feet change from inlet to the exit, and we have 5 sections in this transition channel. So that, for example, we will have 6 feet change. So from here to here, let's say we have 1.5, 1.5, 1.5, and 1.5 change. So this means it is going linearly, and we will have 10.5, we will have 9, and we will have 7.5. Similar to this one, so for example, for the elevation, the change in the bottom elevation is 8.8, it is not visible. So it is 8.84, and we will see for different changes from inlet to exit. So for example, 2.21 feet change for each section, and this means 8.84 minus 2.21. We will just apply the same thing for this side. So the idea is just gradually decreasing all of these values based on the inlet and exit values. And here we have gradually increasing values. Okay, so this is actually one service profile for this transition channel.